One of the most difficult challenges I face is having anyone consider my model seriously. Right now, the smartest people in the world are convinced, the leaders in physics right now are all the vast majority of them are convinced that the expansion of space stops the boundaries of galaxies, and that most of the universe is composed of dark matter and dark energy. The matter that makes up the universe is basically insignificant, roughly 4%. So here I am, one insignificant person, facing the established battalions of physicists who are convinced they are right. Now, this is no small problem. No one wants to discover that the universe that they've kind of figured out is wrong. The current leaders in physics have received prizes, Nobel prizes, or have been paid to establish the work that they've done. And to have some other person come along and say, no, you're wrong, it's this way, it's really no different than some person of one faith telling another person of another faith that, no, you're wrong, and I've got proof to show you're wrong. People just don't want to listen to that. And physicists really aren't any different than religious leaders. As much as they say they are open-minded and consider other things, I know for a fact and from personal experience this is not the case. Anything that's outside of what you're comfortable or what you already know they react just like religious leaders. Well, they tend to stick to the people that share their same thoughts and share their same beliefs, and ignore the people that have ideas that are separate. So this is a real serious problem, and if anybody has some idea out there how I can resolve this and how to best to get this issue resolved, to have it seriously considered, I would greatly appreciate it. I know eventually, it may occur after I'm dead, but eventually I know this model will prevail. Now, one of the reasons I'm so convinced of that the present model is wrong is I can prove it to be wrong. And I'm going to start to do that in the next series of videos. And the first thing I'm going to discuss has to do with the cosmological redshift, which I do predict, I do adhere to that. That is a physical phenomenon we should observe, or that should result from the expansion of space. And when you apply general relativity to the expansion of space, light from distant galaxies would lose energy. Their wavelength becomes greater. And this is indeed seen. The farther away we look at galaxies, the redder they appear to be. And again, like as I mentioned earlier in previous video, this isn't a Doppler effect like a car going by going where the pitch changes. This is actually an effect due to the expansion of space, changing the light as it travels from a distant galaxy to be perceived by us. So this is general relativity, a fundamental tenet of our understanding of nature, predicts this relationship, and it is observed. Now, another fundamental tenet of nature is that of the relationships we find in special relativity. Now, a famous characteristic of special relativity is that the faster you go, the slower physical processes slow down relative to a stationary observer. And this is often illustrated with a twin example. One twin sits on Earth, another twin sits in a spaceship, zooms off into space, travels at near light speed for 20 years, turns around and comes back. The traveling twin has hardly aged, whereas the stay-at-home twin has aged 20 years. So now this is an interesting dilemma. So the first, in that it illustrates an interesting dilemma. The faster you go, the slower physical processes go, and if you could reach the speed of light, physical process or change would come to an end. Well, the light from a distant galaxy, when it's traveling to be perceived by us, is traveling at the speed of light. So how can it change? How could its wavelength be greater? How could it have lost energy? It's moving at the speed of light and change stops. Well, general relativity, usually the response to that is general relativity is the bigger model. It's more accurate. And actually, the light energy is, the wavelength or the energy content is following the contours or the dimensional relationships established in a space-time field, so it really isn't changing in a way. It's keeping its relationship to conforming to the structure of an expanding space-time field. But there are other problems. You can massage that maybe a little bit, but it's starting to get messy. Like, you can start to ask, well, where did the energy go of these traveling photons? It's not in the universe anymore, at least not in the observable universe. It's disappeared. Doesn't this violate the principle of conservation of energy? And you say, well, general relativity kind of allows this to occur. But see, you're starting to see chinks in the armor. There's kind of like suspicions that maybe something's not quite right. And where it really falls apart, I believe, is when you look at the equivalency between matter and energy. E equals mc squared. There's an equivalency between matter and energy. If you take matter and you multiply it times the speed of light squared, you'll get the amount of energy or intrinsic rest energy that's available in that mass. If you can take that mass and convert it to light entirely, you would use that relationship to determine how much radiant energy would be produced. Double the amount of mass, you double the amount of energy. The speed of light is a constant. Square a constant, you still have a constant. So basically, energy equals matter. Their two are equivalent. Double one, you double the other. Well, now let's say we go off and we go into deep space and between galaxies somewhere, and we have 1 gram of matter and another gram of matter, and they're equivalent. But we're going to take this gram of matter, and we're going to convert it into light. And we're going to beam it in a laser beam. We're going to beam it way, way far away to some far distant galaxy with a huge mirror and reflect it back. And after a few billion years, the light returns. And we gather all this light back and we convert it back into matter. Well, this light has lost energy in the course of its travel. So when we convert it back into matter, it's not as much matter anymore. The matter that stayed here and the matter that equivalent matter that traveled through spanning space-time field is less. There's no longer an equivalency between matter and energy over the course of time. And I believe this is a real fundamental problem that illustrates there's a serious problem in our present applications or understanding how we use the principles of general relativity, and by confining that expansion of space and stopping it at the boundaries of galaxies, we end up with a fundamental problem. Now, what I'm going to do next is, this is a chink. Now I'm going to show in the next series of videos, there are even more fundamental problems. It is amazing to me that you can so often see, when you listen to the leaders of our current understanding, the representatives of cosmology that exist today, and they will say, oh, all our problems, how wonderful our dark energy, dark matter model conforms to observation. I'm going to continue to show that this is not the case. There are more serious fundamental errors that exist from the problem we have, the model we have now. Maybe my proposed model isn't right, but certainly I'm going to prove that the current one is fundamentally flawed. Thank you so much for your time. I look forward to sharing more information and with my next set of videos. Again, thank you for your time.